So I wanted to just briefly talk a little bit more about the mole and molar mass. And we'll be talking about this at great lengths in the course. So the mole is how we go from the microscopic world, the atom, to the macroscopic world, which is what we live in. And to do that, we create a definition where we say, if I have exactly 12 grams of carbon-12, and again, this is exact, which means I have an infinite number of significant figures. So if I had exactly 12 grams of carbon-12, it's equal to 1 mole of carbon-12, which is equal to Avogadro's number, 6.02 times 10 to the 23rd atoms, 23rd, of carbon-12. We cannot count atoms. They're too small to see, and 10 to the 23rd, if you started counting, you would be here for a few billion years, even if you were counting very rapidly. But we can measure mass. I'm not going to talk about the experimental way Avogadro's number was calculated. There are several ways to do it now. Later, when we cover the gas laws, we'll touch on that a little bit. This gives us a way to go from, again, mass in the macroscopic world to atoms in the microscopic world. And we need that because when we combine elements to make molecules, we're going to do it based on the number of atoms present, not just a matter of mass ratio. In other words, to make water, it's not as simple as taking 2 grams of hydrogen and 2 grams of oxygen to make 4 grams of water. It doesn't work that way. What we need is the right number of hydrogen atoms and the right number of oxygen atoms to combine to make water. And again, chemical stoichiometry is where we're going to really hit that in a lot of detail, that particular subject. Now, for molar mass, if I have an element like diatomic nitrogen, to calculate its molar mass, it's simply the mass that's listed on the periodic table, and in this case, times 2. So nitrogen's molar mass, so 1 atom of nitrogen has 14.007 grams per mole for its molar mass. Well, we need 2 of them. And so that comes out, make sure I get the right significant figures, 28.014 grams per mole. So to have 1 mole of nitrogen that I'm breathing right now, N2 is in the atmosphere, I would need 28.014 grams of nitrogen. And that gives me exactly 6.022 times 10 to the 23rd molecules of nitrogen, because N2 is a molecule. If it was just N, an atom, that would be a different species. Something like hydrogen, I'm sorry, like helium is monoatomic, so it would exist just as an atom, a free monoatomic species in the gas phase. Specify that that's in the gas phase. By the way, for mass measurements, molar mass, it doesn't matter what phase it's in, whether it's solid, liquid, or gas, you end up with the same value. But just to specify, since I am talking about a couple gases right now. So in the case of helium, 1 mole of helium, and I'm just reading this right off the periodic table, is 4.003 grams per mole. Look at the consequence of this. 4 grams of helium is 1 mole, but I need 28 grams of nitrogen for 1 mole. So even though the relative number of particles would be the same, the mass is very different. So 4 grams gives me 6.02 times 10 to the 23rd atoms of helium. 28 grams of nitrogen gives me the same number of molecules of nitrogen. And we'll see this is going to be very important when we start reacting different chemical species together, because we have to take into account their relative masses when we start making chemical compounds. And again, that will be in the next chapter on chemical stoichiometry. So I wanted to work through some of the problems on the mole concept in the handout that I gave you. And for the first problem, I asked you to calculate how many moles are in 50 grams of the following compounds. So, the first problem is calculate the number of moles for 50 grams of oxygen, O2. The formal way to set this up, we have 50 grams of oxygen, diatomic oxygen. And we want to calculate how many moles of O2. Notice I'm setting up a dimensional analysis table, just like I did for English to metric unit conversions. So what we need is the molar mass of oxygen. 1 oxygen this way. An oxygen has a molar mass of 16 grams per mole. Depending on the periodic table you're looking at, it could be 15.99999. But I'm going to round to make this simple. Well, for O2, we're going to obviously need to have 2 of that. So O2 32. So for diatomic oxygen, it's going to be 32 grams per mole, because we've got 2 of them. So 32 grams of O2 is equivalent to 1 mole of O2, of diatomic oxygen. Again, this 16.00 grams per mole, you do not have to memorize that. That's why you have a periodic table. Whether it's the handout I gave you or your textbook, that's fine. Grams of oxygen, the entire unit, cancel. Now I'm left in moles of oxygen. So, pick up the calculator. And I get 1.56. Whoops. My calculator's dying in the dark. I get 1.562 moles of oxygen, but 1, 2, 3. I only had 3 significant figures. So we round that to 1.56 moles of O2. Part B of the first problem. So now we want to calculate the number of moles of 50 grams of CH4. And we'll see that CH4 is, its name is methane. Right now, we're not going to worry about organic nomenclature in this course. So, how do we get the molar mass of a molecule, of a compound that has more than one element type? Carbon has a molar mass of 12.01 grams per mole. And again, just looking at the periodic table, hydrogen has a molar mass of 1.01. I'm going to round significant figures, grams per mole. The periodic table has hydrogen's mass to a more accurate degree, but now we're going to need 4 of those, right? So that should be 4.04 grams per mole. Okay, we have to take into account the chemical formula. 1 carbon, 12.01 grams per mole, but 4 hydrogens, each weighing 1.01 grams per mole. So we just multiply by 4. So my total is going to be 16.05 grams per mole. So that is the molar mass of methane. Now we want to convert this to moles. I'm sorry, we want to convert 50 grams of it to moles. So to do that, $50 grams of CH4 of methane equals how many moles of methane? Well, 16.05 grams per mole gives me 16.05 grams of methane for 1 mole of methane. It's a 4. And they cancel out. So 50 divided by 16.05, and this gives me 3.11 moles of CH4. And I'm rounding to keep the right number. And for the last example I wanted to work through for calculating moles given a mass. So if we have 50 grams of C6H6, which is benzene, again, right now don't worry about the nomenclature, how do we calculate, or how do we convert that to moles? So C6H6, carbon has a molar mass of 12.01 grams per mole. But now we've got 6 of them. So we're going to have to multiply that by 6. Oops. 12.01 times 6. So that is 72.06 grams per mole. Hydrogen has a molar mass of 1.01 grams per mole. And we also have 6 hydrogens, so we're going to multiply that by 6. And that gives me 6.06 grams per mole. So now we just add them together. And that gives me 78.12 grams per mole for C6H6. So this is the molar mass of C6H6. If I have 78 grams, I would have 78.12 grams, I would have 1 mole. We have 50 grams in this example, so we should obviously expect to have less than 1 mole. In some problems, I will give you the molar mass and then expect you to work the problem, whatever I'm asking for. But in most of the problems, I won't tell you the molar mass. You'll have a periodic table, and my expectation is that you can just calculate it yourself. It is something that you need to get practice with because it's not difficult, but it is a little tedious depending on how large the molecule is. So you don't want to be scratching your head of how do I calculate this molar mass when there's actually a much bigger problem that you're trying to work through. So take the time, work through the homework problems, and get familiar with molar masses. So we have 50 grams. Now we actually solve the problem. 50 grams of C6H6. And we want moles. Of C6H6. Squeezing that in there since I don't want to be out of the camera's range. Again, molar mass. So 78.12 grams of C6H6 is 1 mole. C6H6. Notice I'm actually writing out the formula as part of the unit. It is good to be that systematic when you do it. In this particular problem, if I just wrote grams per mole, it mathematically would work out. But when we do balancing chemical equations, it's very easy to forget which species you're talking about. So it is worth the time to actually write out C6H6, C6H6, which grams cancel. Now we have moles. So 50 divided by 78.12 gives me 0.46. Oh, that's sloppy. C6H6. So 0.640 moles of C6H6. 3 significant figures, 3 significant figures.